Linear regression. What is linear regression? This is a statistical method which is used for modeling the relationship between a dependent variable, we'll call it y, and one or more independent variables, we'll call it x1, x2, x3, and so on. So we'll have these independent variables depending on which you have to find y. So y will be a function of x1, x2, x3, and so on. Let us take an example. Say you want to predict rain depending on different other weather conditions. Let's say you are a very experienced weather forecasting person and you want to predict rain. This prediction is y. So it will be a function of various factors. What could be the factors? Maybe temperature, humidity, wind speed, air pressure. So you'll consider these factors, and depending on these factors, you will be able to say that there is some 30% of chance of rain today, or maybe 75% chance of rain today. So you will be able to say this depending on these factors. This is where linear regression comes in. Why is it called linear regression? Because this function, it should be a linear function. It should not have polynomial terms. The higher order terms should not be there. So basically, you are trying to find the best fitting linear relationship. So in two-dimensional space, a linear relationship is depicted by a line. That is, if this is y, this is x. If you can draw a straight line, that is a linear relationship, right? This is a kind of supervised learning. In the previous lecture, we had seen supervised, unsupervised, and so on. So what is supervised learning? You provide the data, you provide the corresponding labels, and you make the model learn. So here you will provide the data, which is temperature, humidity, and so on. And you will also say when the value of temperature was this, when the value of humidity was this, on that day, rain was this much. And considering that, how much is the chances of rain today if today this is the temperature, this is the humidity, and so on. That's how you make this model. In order to understand this from scratch, what we'll do is we'll take a very basic example, and from there we'll see how we can form a line and how we'll convert this into a machine learning problem, and then we'll slowly understand linear regression, how it can be solved, and so on, right? So let us take a very basic example. Say you are pushing a trolley. Let's say you are here and you are pushing a trolley. This is a trolley which you are pushing. So let's say this trolley is 1 meter long. Okay. So when you are at origin, I'll depict this in a graph. When you are at origin, this is you in x axis and trolley is in y axis. Okay. When you are at 0, trolley is already at 1, right? When you are at point 1, trolley would have reached 2. This is 2. This is 3. When you are at 2, trolley would have reached 3. So this is how this relationship goes. And here, because this is a linear relationship, you can plot a line. That is, you can plot a line through here which depicts the relationship between you and the trolley. So once you plot this line, if someone comes and asks you, when you are at 99, what will be the point at which trolley is in? You can say, if corresponding to 99 in this line, the point is 100. So the trolley will be at 100. So in order to do this prediction, you should be able to draw this line. Now, normally, how would you go on with this task? Let's say I asked you to make a program. Let's assume you don't know machine learning at all, and you are simply making a program. How would you make this program? In traditional programming, how would you make this program? You know the line equation of a line is y is equal to mx plus c. So you have the value of x. If you find m and c, then you can make an equation. And from that equation, you will be able to find the value of y given the value of x. So first thing, you will write an algorithm in which you will write steps in order to find m. What is m here? From 10 standard knowledge, you would be knowing that m is the slope of the line and c is the y-intercept. This is the y-intercept. So first you will write an algorithm where you will write the steps to find m. then you will write the steps to find C. And once you find these values, you will substitute value of C here, then you will substitute value of M here, and then you will find the equation of this line. This is how you normally write a program in traditional programming. But remember one thing that I told you. Whenever you have a chance to write in traditional programming, if you can develop an algorithm and come up with a traditional programming algorithm which you can feed into the computer and find the solution, never ever think of using ML. This is the first thing that I told you. So here you are able to use traditional programming because these points are right on the line. All these points are fitting right on the line. What if the points were here and there scattered? That is, there is an underlying regularity which you can approximate with this line, but the points are not exactly on that line. It is here and there. In that case, using these points, you won't be able to find M and C like this. Instead, you will have to approximate those values. This approximation is where machine learning will come into picture. So just to make you understand how you don't have to give the logic of M and C in order to machine learning, let's see the problem that you just solved of finding y equal to mx plus c. What would have happened if you were doing the same thing using machine learning? Let us see that. I'll just delete this off. If you were dealing with machine learning, then instead of giving the equation y equal to mx plus c, what would you say? You will tell the computer that see, this can be found out by solving y equal to w1x plus w0, where w1 and w0 are constants. You won't tell it that w1 is the slope and w0 is the y-intercept. Instead, you would simply tell it that there are two constants, w1 and w0. You just find out what it is. I'll give you data. I'll give you corresponding values of x and y from historical data or the points that you have here. From that, you find out what is w1 and w0. Once you find out, then for the new values of x, I should be able to derive the values of y. So in traditional programming, for example, if for this line, you know this theta is 45 degree. So slope m would be tan 45. So you know m is equal to 1. Similarly, this y-intercept c is equal to 1. So the equation would be y is equal to mx plus c, where m is 1, c is 1. So it will be x plus 1. So this is how you did it in traditional programming. In machine learning, you simply tell it that it is w1 and w0. You don't use this logic saying this here it is theta is 45 degrees, so m is 1, or here the distance is 1, so c should be 1. This logic you don't feed into the computer. Instead, you just provide data. Let us see how this is done in reality. So let us consider that you have n different observations. So I'll denote it by x, where these are the n different data points that you got. Let's say you found x1, x2, x3 up to xn transpose. Why am I writing transpose? Because normally when you want to write n points, you write it like this: x1, x2, so on up to xt. So this vertical writing would take a lot of space. So instead I'm writing transpose here so that you understand it's in vertical. And then t, let us say t is the target. That is the value of y. It should be, let's say, t1, t2 up to tn. So t1 corresponds to the value of y when x is x1 and so on. So I want to introduce to you to one very, very important concept here. This is very crucial. You need to concentrate really well because this statement that I make here could create a bit of confusion, but I do believe that it's important that you get introduced to this right now so that you stay very clear on what is linear regression, what all comes under linear regression, because linear regression is a very basic and a very crucial concept in machine learning. So you should be at least very clear about what it is right from the day you start with it. So considering any of the standard textbooks, till this point I told you that this relationship has to be linear. That is, it can't have higher order quadratic or any higher order polynomial terms. That is when it is linear. That is, you cannot draw curves. You can only draw lines in a linear relationship. This is what I told you till this point. But coming to any of the standard textbooks, the standard machine learning textbooks that are followed in IISc or in any of the top IITs, one would be Bishop, that is Pattern Recognition and Machine Learning by Christopher M. Bishop. Similarly, there is a statistical learning book by Tipshirani, and there is Murphy's book on machine learning. So coming to these books, for example, if you take Bishop, Bishop clearly states that if you have an equation which is having higher order polynomials, let's say it is depicted by w0 plus w1x plus w2x square plus w3x cube, let's say it goes on like this. In this case, this is non-linear on x. So you would think this is not a linear model. But Bishop says that this is a linear model because even though it is non-linear function of x, it is a linear function of the coefficients. See, what are you trying to find here? You are trying to find coefficients, the w1, w2, w3 and so on. This is a linear function of these coefficients, and because of that, this is a linear model. That is, even though it is non-linearly dependent on x, it is linearly dependent on the unknown parameters, which are the coefficients w's. And because of that reason, this is a linear function. This is what Bishop says. Similarly, if you see Tipshirani considers polynomial regression as a special case of linear regression. That is, coming to all the standard textbooks, they consider all the higher order regressions under the same umbrella of linear regression. This is the whole point that I want to make. See, tomorrow if you are, let's say, sitting in an interview, and in that interview, if someone asks you about linear regression, or let's say you are solving a multiple choice question and you have one option as linear regression and another option you have as polynomial regression for a higher order term, you have to choose polynomial regression only, no doubt. The point I'm saying is all these are considered under a larger umbrella of linear regression. So for all standard purposes, when you say linear regression, you should consider that it includes not just the linear terms, but also those ones which are non-linearly dependent on x, but linearly on the coefficients. And now you will have this doubt that coefficients will always be linear. What is the point of writing w2 square? Because anyway, it's a constant. So would that mean all regressions are linear regression? No, that's not the case. There is exponential regression, there is logistic regression. These things come as different. The only point is all the polynomial regression, those comes under the umbrella of linear regression, which means we'll include the concepts of curve fitting inside regression. That is, if you want to fit some curve like this with a lot of points, this concept would come under the umbrella of linear regression only. This is the whole point, right? So let's proceed with this. We already said that we have n observations. We are considering that we have n different observations. So this is for learning purpose. So what we will do is, we'll first say that we are considering this particular distribution. Let's say we'll take sine 2 pi x. So sine 2 pi x graph will go like this. This is sine 2 pi x. Why did I consider sine 2 pi x specifically? Because sine has a cycle of 2 pi. You would be already knowing about sine x. So for that reason, I'm considering sine 2 pi x. Here, what we will do is, what we want to find out is this curve, the curve of sine 2 pi x. This is what we want to find out. But we've already declared that we are using this curve, because here our purpose is to learn. What we will do is, we will generate a lot of data points around this point, around this curve. So this will provide us points which actually belongs to sine 2 pi x, but have some noise. What we will do is, we'll add some noise to this function, which means the points generated would be slightly above this or slightly below this. Points will have an underlying regularity, and this regularity would be sine 2 pi x function. This is what our whole concept is about, right? So let us take this function and say you generated this. So we have an underlying regularity which is a sine 2 pi x function, and we want to approximate this to a curve. So the curve is this. Let's say the equation of curve is y of x w. So what is x? X is our input, that is, this is x, this is y. X is our input, and w is the coefficient. So w1, w2, w0, these things you have to find. So we'll write this equation as w0 plus w1x plus w2x square plus so on. So how can you write this equation in short form? That is, instead of writing this large piece of thing, you can write it as y of xw is equal to summation over from j equal to 0 to n. Let's say this is an mth order polynomial, then that is this is up to wm x power m. In that case, you're summing from 0 to m wj x power j, right? So this would depict, this is a shorthand notation for this whole equation. That is, this will have all the terms from j equal to 0 to j equal to m. That is, w0 x raised to 0. X raised to 0 is 1. w1 x power 1 plus w2 x square plus w3 x cube plus up to wm x power m. This is what this depicts. Let us see how we will find the values of w. In order to find the values of w, we need some sort of a condition. And one more thing, see here, this function is non-linear in x. But as we told earlier, this is linearly dependent on the coefficients. Coefficients are the unknown parameters that we want to find. This is linearly dependent on the unknown parameters, which are the coefficients. And because of that, we will call this a linear model. So we are doing this curve fitting using this linear model. Our task is to find the wj's, the values of all these wj's. For that, we will say we have a condition. That is, we want to make a curve which best fits all these points. How can you best fit all these points? For that, you want a curve such that if you see the distance between each of those points and this curve, let us say you took all these distances, distance from all these points to the curve, and you add up all these distances, that total sum should be the least. That is, if let's say I can find some other point, let's say something like this, some other curve, this curve, let us assume that if this curve has lesser distance from all the points compared to the yellow curve, in that case, this green curve would turn out to be a better approximation than the yellow curve, right? So we want to find the best approximation. For that, what will we do? We have to find the curve which has the least of this sum of distances. Here, if you simply take the sum of distances, what will happen? Just think. If you simply take sum of distances, the sum in the for a point which lies above this would be positive. I meant the distance, that is the difference. How would you find this distance? That would be y minus t, where y is what you observed in this line. Y is what you derived from your equation, that is the line that you're considering, and t is what you actually observed. For example, according to your curve, point lies here, but maybe the actual point is lying here. So this is the difference, right? So that difference is y minus t. But this y minus t will be positive for a point below and negative for a point above. Now, if you add this up, these would cancel each other. To avoid that, that is, if you take a point below the curve and point above the curve, the value would be positive for one and negative for one. And these would cancel each other. To avoid this cancellation, what you do is you will square these terms. So you call it sum of squares. Your error function, you call it error because error is what you want to minimize. Your error would be y minus t, and if you square it up, it will always be positive. Now, if you add all these error terms, it would in total be a positive value. So how will you add all the error terms? Let's consider all the error terms. E of W is equal to sum of there are totally, let's say, n data points. So n is equal to 1 to n. From 1 to n, you are summing up y is your observed value, y of x n w. This is your observed value that you found from this equation, minus t. T is the actually observed value, that is the actual point, that is t that you observed. So y minus t the whole square. This is what you want to sum up. So when you sum from n equal to 1 to n, for each point you see what is y. Y is what you found from the curve, minus tn. That tn is the actual value of that curve. Then you will see what is the distance. This distance is what you get here. You will square that value and this is your error. So in the sum of squares term, you will have a half here. This half is for mathematical convenience, that will be clear to you later. So this error term will be half of the sum of or square of all these terms. So this is what you want to minimize. Let us say how will you minimize this? So W is what you want to find, W, and this is a quadratic function of W. Why is it a quadratic function? Because Y is a function of W, as you know from here, and this whole thing is squared, which means it becomes a quadratic function. If you minimize this whole function with respect to W, then you will find W star. So W star is the value of W which best approximates the curve to all the data points. So this value is W star. How did you get W star? By minimizing this error. You wanted to minimize this error. When you minimized, you found the value of W star. W star will have values of W0, W1 up to Wm when you are considering an mth order polynomial. So these values, when you substitute in this equation, you will get the value. You already know the value of W0, W1 up to Wm, plus you will be given the value of x. If you know the value of x, if you already have the values of w's, you will be able to find the value of y. That is the whole purpose of regression. The mathematical derivation, we'll take it up separately in a different lecture. That is when we revisit linear regression, because at that point we would already knowing the required mathematical concepts. Moreover, you will be more familiarized with these things. So at that point, when we do the derivation, you would feel like this is a very basic thing. It's a very simple thing. So it's better we take up the mathematical derivation at that point, where we'll derive the equation for linear regression and we'll see how linear regression works mathematically. With this lecture, what I want is you should be having a very clear idea of what is linear regression and how it is working. What is the error? What is it that minimizing? This thing you should be knowing. Now, exact derivation that we'll take up later once we are clear with the other concept. We'll go through some other mathematical concepts about the concepts of probability of different distributions. Once we cover those things, we'll revisit linear regression. Moreover, this idea of linear regression, this is introduced here because for our coming lectures where we cover other concepts, this idea of linear regression, we'll be using this in order to learn those parts. So there it will become easier for you. Okay.